Maybe it's stopped for some reason. Sorry.
And we don't have to store everything for our file system in like physical memory. We can actually have it in
Yeah.
memory.
Yeah, in main memory. Yeah.
Is that how a lot of file systems do it?
Is what?
Is that how a lot of file systems do it?
Well, only file systems that lose all their files when you turn off the computer.
Oh, that doesn't sound like a very good file system.
Well, you can make it a better file system.
Well, you could also just store it. You could store like your entire structure representing the file system into main memory before you shut down. I guess. I think.
Well, main memory is going to lose it when you shut down.
Or well, I mean, before the file system closes, though, it just stores it all in physical memory and then shuts down.
Oh yeah, like copy to the hard drive
Yeah.
before you go. Yeah, yeah, you can do that. You can write to hard drives and other file systems, including the root file system for the machine from in the kernel. And so you could say, well, as part of the power off sequence, we're going to copy all the file off to just like the root file system, which is storing your file system contents in a different file system, and then you just load them back into main memory when the computer starts again. And then you're going to name it something like Turbo FS to emphasize that it's faster when the computer's running than the other one. If your cat walks along and pushes the power button on your computer, it's going to lose data. But there's always risk in life, you know. Regular file systems can lose data in that circumstance too.
Except for mine, because distributed file allocation table, it's very hard to lose all your data that way.
Yeah, it would be. But if it was in the middle of writing a sector, then
We would just move on.
we'd just move on.
We'd just
Yeah, it
move
would
on.
move on, wouldn't it? Yeah.
That's why it's so awesome.
Yeah. That's pretty resilient.
And I thought of a way to like make it faster and just add a defrag method.
Mm-hmm. Yeah, that should be fast. And seeing you got, you don't have to worry about like seek time. You should be fine.
Right?
Because in a normal file system, you spend a lot of time worrying about whether or not you're making the arm jump around on the head, and so yeah, you don't have to wait for that. Okay, so the extra credit schedule should be up on here, or extra credit rubric. There you go. I hope somebody does this bottom option.
It's happening.
Okay.
We're just going to get the keylogger working for both USB and PS2 keyboards.
Okay.
File system sounds fun too.
Yeah. So let's see, October, what is it today? Did I forget to post those two? Like I said, it's tradition. Don't mess with tradition. Okay. Okay, so Project 3 was the first thing to talk about, and we did that. We'll talk about file systems a little more in the coming time in regular class too, but you'll probably be more of a file system expert if you go for the alternative there. We'll get to that and they'll be like, yeah, I figured that out. So I'm going to talk about process 1 and fork real quick. This is where chapters 3 starts. And then talk about shells for a while. So process number 1, and the way you get processes in a Linux style system is you call this fork system call, and fork splits your process in 2, and then you have 2 of them. And so last time, where we left off on our tour of the Linux kernel, we were just getting to the point where the kernel stops running a process at priority level 0 and moves to priority level 3, like a user level process. And that's where initialization will continue. And that's where fork is. So I want to talk about the shell, because we're I was looking at this and I was like, we'll talk about fork and starting processes. Yeah, that's exactly what the shell does. And in fact, it's what the shell does all day long. So the shell follows a really simple algorithm. And basically, when you hit enter, it takes your line of code and, well, code, command, whatever, and expands wildcards, so any kind of shell variables you have, and sets up pipes, and then executes processes. And this is generic. I mean, it does this on all operating systems, really. There's a definition out there for a POSIX compliant shell. And so POSIX shells have certain features on using pipes and redirection, stuff that the shell is expected to do. And then other shells like Bash or ZSH or C shell or whatever add on to it in various ways. The Windows shell was originally a kind of a Unix Lite version. DOS came about partly as a Xenix derivative. Microsoft owned Xenix, which was their version of Unix, and made DOS as kind of a light version of Xenix for the home user. And they were envisioning these things coming together at some point, but they never did. And they eventually sold Xenix back to the Santa Cruz operation SCL. Oh, wait a minute. So this is how shells work on any kind of platform. So I want to take a look at a shell, and it's not going to be Bash, it'll be a MSH, mini shell. And I kind of know how this one works, so that's the reason for the pick here. And I think I have it on my software. Oh yeah, perfect. Okay. So if I run this, this is MSH, and so I can run commands. It supports pipes. Let's see, grep for *C. It doesn't support the arrow apparently. There's all the C ones. The expansion there, echo everything. It doesn't expand a star. It doesn't do everything that Bash does by far, but it does a lot of stuff that you'd expect from Bash, like pipes. It does redirection too. So if we wanted to put everything through here, grep for say a C at the end of the file, like that, we're just going to get our stuff from the end, and doesn't support up arrow. Grep, say, put all of this stuff into a file, results. Okay. And that was a little odd. It should have all gone into a file called results. It certainly disappeared. Well, that's interesting. And yes, the arrow keys don't work. Let's get out of MSH. It's actually not that fun to use. Anyway, so this is what we had to do for Unix programming class when I went to school. And so, yeah, it's a CS352 assignment. And we don't really have any equivalent of CS352 here, and I really kind of feel bad about that. Like, it's, when I was going through, we went one of the levels, in the 300 level, we'd have like a Windows programming course and Unix programming course. And you learn how to write Windows software and Unix software. And then later, the equivalent of this class would come. This is a hybrid of, at my old school, it would have been a hybrid of CS4 something operating systems and CS513 device drivers, which is one where we actually write kernel code. And yeah, I'm pulling graduate level stuff down, and you guys are doing awesome and asking for more of it, so that's good. So anyway, oh yeah, so we don't have this class for you to write this thing, because our Linux class is like how to use Linux. Oh yeah, so this is the main program for the shell, and you can give it an argument, and the argument would be a script. So you can run like Bash and give it some kind of command, and it runs that, and that's fine. And so you have some kind of source to get commands from, whether it's from a file or from standard in. And standard in is kind of the standard here, but it might be that we end up opening a file, and that's where our commands come from. We haven't talked about file descriptors much on Unix. File descriptors describe files and things that look like files. So, file is obvious, but standard input, the stuff you get from a keyboard, that's a file in a Unix type system. And so we have this, this source here that can be a file or standard in. Standard error is also one of these, and pipes are file descriptors, network sockets, stuff in /proc, devices, all this stuff is represented by file descriptors. And so we talked about like files and inodes before and how these things have inodes. Anything that has an inode is going to be able to have a file descriptor. And a file descriptor is just a number, that's it. It's an entry in a table that will tell the kernel which file to look at, basically, which inode to go for. So it's just a number of an inode, basically. But there's a open file descriptor table for each program. So when you run a program, it has a table of files that it has open, and so it's your file descriptor is something that's handed to you as an index into that table. Okay, so we may or may not open a different source here. And at exit, cleanup. Yeah, it does some cleanup. Okay, so then we just kind of enter this infinite loop. And that's kind of the main thing here. And so this is the algorithm I was describing. We might have to wait if we got a running process, and we might have more than one running process, because if we have some kind of pipe and it's got like 3 different pipes from one thing to the next, we're going to have 3 different programs running. And so this thing is going to have to keep running until all of our processes are done. And once those are all done, then we can present the prompt for the user again. I realize in Bash, it stays listening for certain keystrokes like Control-C or Control-Z, and this one doesn't handle stuff like that. But there would be some other stuff in here for Bash. Anyway, so if there's more processes there, we need to wait for them, and that's that. Okay, so use prompt thing. You can set an environment variable for your prompt. You can do that anyway. This is like Linux class stuff, but if you export ES1 equals dog, then you know, that's my prompt now. Okay, mini shell supports the same thing. And so anyways, use prompt there, and so you can start that, and I'm going to print that out. And then we just need to get what the user has entered. And so we're getting that from our source, be it a file or standard input. And go ahead and get something there. Okay. So fgets, we'll go ahead and get something and put it in buffer. And it returns, I believe, the address of where it put it, so the address of buffer. And so if it doesn't return a buffer, that's bad and we need to break. And turn handler here runs the command. And if turn handler doesn't work right, we're returning the first character of the buffer as our exit status. And I think turn handler uses the first character of the buffer to stick a return status in. So anyway, that's the basic prompt algorithm. Okay. And finally, if we're not at the end of the file here, then we got a read error of some sort. Okay. That's it for the main program. So this turn handler, probably in here. Okay, there's a turn handler. And so basically it might get an error from processing a statement, and the error is equal to process normal, which is just defined constant somewhere. We return process line. Okay, so P statement, then process line. Okay, that one's not in here. That one is actually in here. This is spread between a few different files, so P statement somewhere else. Okay, so process line is a couple of different ways it can be called, but the basic point in process line is to handle any kind of shell expansion and anything that needs to be done. Okay, so checking our input file descriptor and output file descriptor. And so these inFD and outFD, these can be specified. -1 on these two. If either of them is -1, we're going to go ahead and copy our line to a new line, our line that we're going to run. And I think that handles the case of reading from a pipe. And then we want to go ahead and expand everything. So expand is going to look for stuff like shell variables and things. It's an expand.c. And so expand, we take a line and we expand it, and we got some kind of expanded length. And so anyway, it's possible that we expand it and it gets too big. But that usually won't happen. Because the star expanded, you know, it's got a certain amount of space in it. And if we overrun it, then that's bad. Okay, so this is just a loop that copies things in normally. It's got an error there if it's full, but then no, there's a lot of stuff that just gets processed normally that doesn't take any code, and there's a lot of stuff that gets processed funny that does take code. Process normal over here, it just makes a copy and moves on to the next thing. That's it. Okay, so cases could be in quotes. If it's in quotes, then we start treating it like it's in quotes. And treat it like it's in quotes has various meanings as we go. Okay, and so it might be a opening brace like that. And so if we got an opening brace, we're going to go look for the closing brace there. So as we go ahead and process this stuff normally. Okay, we're looking for an environment variable here with get E and V. If I remember right, the braces, oh yeah, look at that. We're in case $ here. We're looking at a shell variable. Okay, so if our shell variable starts with one of these things, then we have to look in, wherever we're looking. I forget what that one even does. Pound is the number of parameters to your script. And so it's just going to get that value and stick it where it came from. Question mark is the status of the last command. So you can see the last exit there. $, I forget, oh, PID, process ID. And so that's getting our process ID and putting it right there. And then finally, we check to see is it a digit. And if it's a digit, then we need argument number such and such. Okay, tilde. Tilde means your home directory. Well, that's one thing it can mean. It can be somebody else's home directory if their name's after it. And so what we have to do here is go and figure out what the home directory is by looking up your home directory and the password file. So let me back out of here for a minute and look at etc password. You can see that for the most part, people have home directories that are just kind of where they are. It's like my user Seth has home directory at home Seth. Well, this isn't actually quite universal in every case, because root, for example, they're not a home root, they're a /root. The daemon home directory is user sbin. And it's possible that nothing's at /home, you know, they can be wherever they are. And so that's why we have to go look up in the password file where it is. And there's this these helper functions, get the work directory for the user and that kind of stuff. So this gets the password directory entry in this password directory struct. And I suppose it's possible we could have an error. And yeah, okay. So with this whole name thing, you might have a username there. So the case we're talking about here, that's back here. Okay, so if we say echo and we expand it to say tilde root, we're going to see the root's home directory. And so anyway, that's what we're handling here. Because there's going to be a name coming next, and so we just copy it out, which isn't very interesting. And go look it up and see what it is. Okay. Pound sign. Go to end loop. I don't remember what pound sign does. Quotation marks. So if we see a backtick and like a single quote, we actually ignore it. But otherwise, this here, by the way, this bracing, this restricts the scope. So these variables here only exist within these braces here, and that's why that stuff is there. Okay. Anyway, so if we're not in quotes, we're going to go and take care of trying to find a match for this thing, because whatever it was in quotes, and this is the backtick expansion, I believe here. So like if we do MSH, okay. Now ls gives us this output here. If we say echo and in backticks ls, it's going to go run ls and put all of the output where the backtick thing was. And bash does that too. So basically what we got to do is go and process our line again, like start the whole procedure over recursively. And you can probably double the recursion with some creativity about hiding these things with quotation marks for the next time. Okay, and then default is just go ahead and pass things on. Okay, and so that's what's done for expansion on a shell. And so when we say expand on a shell, we don't necessarily mean that the command line gets longer, because it could actually get shorter if you have some long command that boils down to a number or something. But anyway, yeah, usually it means expansion. So I'm curious. Okay, so ls, sure, ls /home Okay, there's everything in the home directory. But suppose we want to do ls, say, our working directory. pwd gives us our working directory, so if we say echo ls, in quotation mark, pwd. Bash didn't like it. Wonder if MSH likes it. I don't know. Let's see. I guess it probably just didn't spell it somehow. Line too long. Not sure why the line is too long precisely. But it doesn't look like we can do that. What about using escape? Yeah, probably not. On this one? Sorry, I'm interrupting the lecture here by tangent because I'm curious. Hey, I think Bash took that. So if instead of pwd we return some other kind of directory, well, it appears that actually you can nest those if you can get everything past the shell expander using like escape and things. Well, that's good to know. I don't know what it's useful for precisely at this exact moment, but it is doable. Okay, oh yeah, so continuing with the grand tour here. Okay, so we know what the expand does here. Where's expand? Expand right up there. And so there's the possibility of making the line too long. I suspect we sent it infinitely recursive somehow because that wasn't really a case that I thought about at all when writing this thing. And okay, IO move scan. So IO move scan takes care of other stuff, pipes and whatnot. And send pipe off. Okay, so there's a couple of different options here, but one of them is IO move scan. So this is looking for, again, quotations matter, so we have to process things differently if we're in quotes or not. We're looking for a pipe or redirect. Pipe calls us pipe at function, we'll get there in a minute. The greater than sign, less than sign, etc. calls output redirect and input redirect and that kind of thing. Of course, the two greater than is like a redirect standard error. If there's not any of this, so basically if this is not a greater than sign, we'll just continue, or if we're in quotes, or if this these other conditions are true. Let's see we did that. Then we want to go into a redirection. Okay, so redirection happens like that. Okay, this whole pipe at thing. Well, we're going to have two lines to process because when you have like a line, or a line and then a pipe and then another line, what you have is two lines. And so you have to take everything from one side and send it through the pipe to the other side. So we actually have two separate commands that need to be run kind of separately. So that's another thing that just kind of recursively starts this whole procedure running again because we got to go do both sides. And the whole pipe at thing here. Pipe makes pipes. We might play with pipes a little bit more some other time. Basically, you say you want a pipe, and you give it some file descriptor locations to say file descriptors for it, and it'll either return an error or it'll set up a pipe between these two file descriptors that it gave us. And so then we just go ahead and set these things up. So one of them has an input file descriptor here. That's what we're reading off of, our source, like a file or a keyboard or whatever. And this side over here is going to be the input side of this pipe. And on the other side, we're going to be taking the output side of that pipe as our input. And then the output goes wherever the output was currently going. That handles one pipe. If we run into another pipe, this thing is going to recursively happen on the second one of these. Because this will scan until it sees a pipe, and then it'll recursively call the process line on both sides, and then we might end up doing the same thing again later with the other pipe, and that's fine. In this whole I+1 thing, we're on this line, and I is our current position, and so I+1 is just like one character past the pipe. Okay, so that's the pipe at one. This other stuff does kind of the same sort of thing. We want to open files for input or output. In this case, we're going to open something, and then that'll be our new file descriptor for whatever way the output's going. And we have to clear out that from our command once we've done it. Okay, and and you can use two of these things if you want to append. And so we got to change our flags here when we open a file for output, because we need to do output or append or truncate, just replaces the file. And that handles that part. Okay. So that's IO move scan and doing that kind of stuff and pipe op. So we're back here, and so we have to parse our arguments. Okay, so that's an arg parse. Where else would it be? And so definition of arg parse. So arg parse takes a triple pointer here, argvp. So it's like a pointer to argv, which is going to be our argument vector. And you can see up there, char double star argv. That's going to be our new argument vector, or argument values. Excuse me, vector of values, whatever. And it's a char double star using calc here, so we can initialize stuff. So there we go. So anyway, we're making a new argv, and this argv is going to be for the command that our shell is about to run. So this is what's going to get handed to its main, and so we have to assemble that whole thing. And quotation marks, these matter because when you see a quotation mark, you end up grouping together all of this stuff. A space is not a separator when it's inside quotation marks. So we have to handle that. And what we're doing here is basically filling out all these places in argv with whatever part of the line matches. And we're setting the last place that we're looking at in the line to 0. The reason we do that is to indicate the end of a string. So the idea here is you start out with some kind of program, and what we want to do is, instead of spaces here, change these to a 0, like a null character, and then we want to make a arg vector here that has pointers that point to that and that and that. But the last one on here needs to be a 0, like a null. And so that's what we're making for an argv. That's what argv normally looks like. Okay, so making one of these structures is really pretty straightforward. And we just go along until we see the beginning of an argument, and then that needs an entry here in argv. And we go along until we see the end of it, and that needs to be turned into 0. And so the result of that whole process is argv. And so then at the end, we change our argv pointer to the argv that we just made and allocated in this function. So this is actually allocating something and returning it. So this is something that ought to be freed later. Okay. So after that whole thing's been changed, notice that we didn't actually copy the text anywhere. We left it in place. Because this one doesn't expand or contract anything, it just stays. Okay, commands, last exit. And it's time to get ready. Well, we're preparing for ultimately fork and exec. We're not quite there yet. So I is less than commands. Okay. So it looks like we're checking to see which, I don't see why we have a bunch of commands on this one. Oh, setting up our last exit and things. So we have to keep kind of a history of which commands have been run. And that's important for like the exit status of the last one and stuff like that. And so we're keeping our history there. Okay, but we're going to have to deal with that more later. Okay, so this buffer. We have to set up some buffering and get ready to fork here. So the buffer, we're just checking to see if we actually have one. and checking on pipes, make sure our pipes are there. And we get down to fork, where we actually do something again. Okay, so fork splits this into two. And so if we have, if it returns a 0, then we've got an error. But it probably won't do that. Well, less than 0 is an error, sorry. Assuming it doesn't, we check to see if we're the child or the parent. And the parent's all the way, way down. But in the case of the child, we need to get ready to call exec CVP at this point. And exec CVP, it replaces the current process with a different one. And it's going to replace, use our argv here. So argv position 0 is the name of whatever the user specified that was going to get run. Argv over here is the argument vector that we just put together, argument values. Okay, so we'll go ahead and execute that. And we have to do a little bit of duplication first on these file descriptors. So when we say dup2 here, and we give it 2 file descriptors, what it's doing is it's taking the file descriptor for the first one here and duplicating it over to descriptor 1. And so that is how we handle redirection and pipes. And so if we're handling pipes here, we want to duplicate file descriptors position 1. We close file descriptors at position 0 right up there. We're opening it at position 1. And if we're doing another redirection, we just want to duplicate over what our file descriptors are, first standard error, whatever. Okay, so once all these things are done and we do exec CVP, we go ahead and print an error here. We know there's an error here because exec doesn't return unless there's an error. Exec replaces us with the other process and off it goes, no error. Okay, so I might have got an exec error. Okay, so at this point we know that the CPID is not 0, because if it was 0, we would have either exec'd or errored, one or the other. And at this point we know we're the child. So you go ahead and check to see if we're using the buffering and pipes sort of thing here. And we may have to do some pipe housekeeping here. We may have to close a few file descriptors we don't need that aren't going to be needed in the parent. And finally, we go wait on the child to finish. And if they're not done yet, then we just add one to running processes, and we can go ahead and head out of here. Okay, freeing the RG there. I mentioned that was going to have to get freed later. Okay, so that actually returns control back here to msh.c. And, oh, we're in msh.c. It returns control up higher in here. So that was going to return through by way of turn handler, because we just looked through process line. Look through process line? Yeah, we looked through process line. And so we're back in here and running back into our loop. So that's what a shell does. That's a simple shell. That's what they do. Okay. So that's that. Now you see a shell. So Bash has a lot of extra features, and for example, it supports up arrow and using the arrow keys and using backspace and other things that people sometimes find handy. Dash actually removes a lot of those features. So if you ever run Dash, I've done this in Linux class. This is what Dash looks like. This is my prompt as it's described to Bash. And I actually ran into a case the other day in my Linux class, and I don't mind covering it here because it's kind of relevant. Okay, so watch this. Echo, opening brace, 0 to 10. Okay, so the shell expanded that into the range 0 to 10. So you can put a for loop on here. You can say like for x in 0 to 10, do, and let's echo, and x is $x, and that, done. Okay, and so you can run a little for loop here in the shell, which works great. Okay. Okay, I changed my prompt because the whole long thing was irritating. Oh, let's go ahead and copy this whole thing in down here. Okay, so it didn't work. And if we echo, 0 to 10, it's just going to echo 0 to 10. Like it doesn't recognize that. Incidentally, if you wanted that, there's this command called seek, which is sequences. And so that gives you a sequence from 0 to 10. And no up arrow support either on dash. So we can say sequence of 0 to 10, 10 with a separator and a space. Maybe it's not dash S. Oh, I can't even do that. Maybe it's dash S. I don't know. Anyway, you can make it work with this. Separator equals. Yeah, there you go. I don't know why it didn't work the other way, but it doesn't. Okay, so dash has less features, a lot less features, and it runs faster. So if you ls-l bin sh, you can see bin sh on this system is linked to dash because dash will run scripts faster. The whole thing about the brace expansion might need to get added to dash at some point. That's not a traditional bash feature. It was added in bash version 3. And if we look at bash on here, we're running version 4.3. So we're a little bit beyond version 3 now. And it's something where if you wrote a script for bash and put your script on Debian, it wouldn't work unless you started the script with /bin/bash instead of bin sh. Oh, yeah. Okay, so shell's not in the kernel, and so it's kind of part of the operating system, and sort of. It kind of has to be there. I mean, operating systems have shells. OS X has a shell, Linux has a shell, Windows has a shell. They all have shells. But anyway, so it's there's a lot of non-kernel parts of the operating system that we haven't really mentioned very much. For example, there's this whole graphical display subsystem. And so on a Linux machine, you're going to have X11 running, or an X server, Xorg. And on top of that, you have a window manager that takes care of saying what windows look like and where they go and how you move them around and how you tell them to go away. And then on top of that is where your applications, graphical applications, programs run. And it's just kind of a convoluted system. I mean, there's probably as much source code in that as a kernel. I haven't looked. So there's that, and there's this whole C standard library. So if you go on here and you say man printf, well, say man 3 printf, you're going to get this Linux programmer's manual entry, and this is the C standard library. This is expected on systems. You don't really have systems that don't have a C standard library on them, and so. On my software release, we're using eglibc, I think. And I might actually even have the source code on here. I have glibc. Maybe they changed from eglibc. Maybe not. Saying I have it right there. eglibc is embedded glibc. glibc is the GNU implementation of the C standard library, clib. And so eglibc is on here. If we find type file name, and something that ends in C, find everything in here, save F. There's all the files, just pass it through grep. Grep for anything that ends in C, there's all the things that end in C, and the word count, everything from that expression. We're going to find out that it has 900,000 lines. So, this is kind of a major part of the operating system in a way. I mean, if you're writing your own operating system, you'd have to spend a long time on a C standard library.
What's the .def file?
The def.
Yeah, I saw that go by.
You did?
Yeah.
Shouldn't have.
That's a better idea.
I just see those.
Huh.
And what flew by. Did it fly by earlier?
Maybe it was earlier.
Okay, like before I did that.
Yeah, before you did that. Were you in a different
No,
direction?
there, test.def.
Oh, okay.
Yeah, I think that's like, test. not C code. Okay, so version set. Here, you can look at one. There you go. That's what a def file has in it.
Oh, okay.
Okay, so glibc is made a massive part of an operating system, and kind of has to be there. And most of the time when you look at stuff in here, it's going to be an implementation that uses other stuff on the system, but people use it to assure platform independence. So if you write some kind of C program and you're like, well, I want this to work on Windows and Linux and OS X, instead of using, say, Unix file descriptors and write, you're going to use printf, right? And then you can run it through a compiler on any of those systems, and it'll be fine. Actually, well, I don't think you can compile it on Linux and run it on. Yeah, it's not gonna be linked right. Anyway, so the whole printf thing, and you know, either everything in manual section 3 basically is implemented in here, and it's useful. Okay, there's a lot of user space stuff for the system that's just kind of there. So initialization systems is how you get the whole system up and running. Once you get more to the user space side of things, you got run levels, and run levels are numbered 0 through 5, and sometimes different numbers than 5 for the top, depending on which operating system exactly. The run levels define different things. Usually, like the highest run level is what you normally run in, and other ones like 0 is going to be don't even have a shell yet, but the kernel's all going and done with its stuff. And so the intermediate ones will have definitions like, okay, you have a shell. The kernel was around, of course, from the previous run level, but now it's got all of its kernel modules loaded, and you know, that kind of thing. And kernel modules do have to get it put in from a user process that goes and initializes all this stuff. So even getting the kernel going does require something in a way of init systems. Yeah, I put a couple of names on there. So sys5 init is the standard way to go, and our book is actually going to tell us about init to some extent. But there's more modern replacements coming out. The reason is the System 5 style initialization. It was reliable and it was easy to manage, but it was kind of slow. And you can boot up a lot faster if you can configure your network interface at the same time you mount your file systems, for example. And if there's like 3 different hard drives on the machine, there might be a lot of mounting to do, and so running this stuff in parallel can be a great idea. Traditional sys5 init, I always found it irritating when I would boot some machine up that wasn't plugged into the network, and it would go ahead and wait for a couple of minutes during the boot sequence for the network card to get a reply from the DHCP server, which obviously was not going to happen. And so anyway, running this stuff in parallel means you can get the user able to log in a lot faster. So there's a couple different competitors for it. Systemd and Upstart are the main ones I've seen lately. Upstart actually came from the Ubuntu side of things, and they were using it for a while. I'm not sure if they're still using it or if they abandoned it. Systemd, if I remember right, Systemd is what's used on Debian right now. It was written by a guy who wrote this audio server called Pulse Audio that everybody hates. And it caused some initial trouble in terms of adoption of Systemd. People are like, we're not going to use something this guy wrote. But it's actually kind of taken off, and it does boot systems a lot faster. And so Software's using it, and Rod's using it. I don't know if this is the system here is. So there's a few different initialization systems. And one of the main things that the initialization systems do is start all your daemons. And so all the daemons are what you get if you type in top here. And you can see all of this stuff that's running that's owned by root and has some kind of name over here, Systemd.
He's been running top for so long.
Yeah, he's been running it for a very, very long time. And I don't think he's actually logged in right. Well, maybe he is logged in right now. I just saw something come through.
Mark's running Kelly Mark.
Yeah, he was running like a WUMP using full CPU for a good while too.
There's like 3 of them.
He was running
Yeah.
like 31 processes or something.
Yeah. Yeah. Anyway, so there's all this stuff running. I saw Systemd there in the list of daemons that was running, and so it's definitely still running. If I look at this system right here, which is not quite as interesting, Pulse Audio is currently running on this system, and I don't see Systemd, but I bet it's in here somewhere, unless they're running Upstart, because they're pretty big on Upstart. Okay, So some of the stuff in here, cron. You usually have a cron system. Cron handles running jobs when you're not around. So you can use cron to run a backup script at 8 in the morning every day. And so usually we want some kind of thing like that running. Swapper, also called sketch sometimes, or sked, I don't know how you say it. This controls swapping stuff. So remember that the memory system is going to use paging. And when you use paging, there's going to be a certain amount of housekeeping in terms of deciding which pages go in and which go out. And we don't necessarily want to do this at the moment that the user is called malloc or something else, because it might be nice to do it in some dead time instead, handle memory management. And so there's actually a daemon to initialize system calls so that the memory manager can go do what it needs to do at other times. And I'm not sure this is actually how it worked on Linux 0.11 that we're looking at, but it's how things work now. And so you'll have some kind of memory manager process that just sticks around and wakes up and triggers some kernel code every now and again. inetd. This looks a lot like initd, but it's got an E there. This is networks, net. This manages network connections that are that happen on the system, and so it's got to listen to all the ports and send things through to the right program. If any program is called a port, and so it runs all the time too. And then finally, syslogd handles logging, and so all the stuff in their log. This is all put here by syslogd. And there's a few different system logging daemons out there, but they all basically do the same thing. Okay, and there's a whole bunch that are on the list. You have a mail daemon and possibly a web server, or SSH, etc., etc., etc. So these are all kind of part of the operating system too. You expect all these functions to happen, and they're not in the kernel, but they're kind of important to making the whole thing work. I don't have the code for all the daemons loaded on here. And the exact set kind of depends on what you're using the system for anyway. Like you might have a DHCP daemon that's serving DHCP, or you might not. Oh, anyway, that's kind of the coverage of the non-kernel part of the operating system. So I can get back to the kernel next time and talk about what matters, I guess. But this stuff is important, If you just have a kernel loaded on your hard drive, it's not very useful. Okay, any questions? Comments? Complaints?
I need to show you my project or lab file, I guess.
Oh yeah, sure.
Show that to you.
Yeah. That sounds good. Some people are sending screenshots, some people are showing it to me. All happens different.